Hello everyone, welcome to the Purnima University. Myself, Mr. Ankit Khandelwal, Assistant Professor from the Department of Faculty of Computer Engineering. We are having a discussion on the course Computer Organization and Architecture, and the topic of discussion is Booth Division Algorithm. And today we are having a discussion on the method which is known as non-restoring division method. The content of the lecture are as follows. First of all, we will have an introduction about the Booth division algorithm. Then we will see some points to remember regarding the algorithm to be taken in an initial steps. Then we will go through the steps for non-restoring division method. Then we will conclude it with an example. We will see how this non-restoring division method works in the processor for the two operands there. The outcome of this lecture on the non-restoring post-division algorithm includes that is understanding about the algorithm, that is how binary division works using the non-restoring method, the step-by-step process of shifting, subtracting, and updating the quotient there. Also, there are efficiency benefits from this algorithm in comparison to the restoring boost division algorithm, which we have discussed in the previous lecture. So why non-restoring division is faster than the traditional restoring method, you will come in after this lecture, and how it minimizes unnecessary restoration, that is making it useful in hardware implementation. So now restoring is an efficient method, okay, is an efficient method for performing binary division commonly used in hardware implementation. So it avoids restoring the dividend, okay, in case of an unsuccessful subtraction. So we have seen in the restoring method, whenever there is a unsuccessful attempt, that means when we are subtracting the m from the accumulator, that is divisor from the accumulator. If accumulator is having a negative value, then we have to restore back the value of the accumulator. So this algorithm makes it faster than the traditional restoring division method, because in this there is no restoring process. So as we have discussed, there are two types of division algorithm. First is restoring algorithm and another one is non-restoring algorithm. Today we are having on the second type of division algorithm, that is non-restoring algorithm. In the last class or in the last lecture, we have discussed about the restoring algorithm there. Points to remember is that first of all we have to decide which operand will be the divisor and which will be the dividend. This will be as per the question there. So we have to convert both the operands to 2's complement representing using x bits. Okay. The points regarding the s bit is that the x bit, the x must be at least one more bit than is required for the binary representation of the numerically larger operand there. So this is the 3 points which we have to taken into consideration before beginning the division algorithm there. Now, the steps for restoring division method is that the first step is that we have to initialize the register, that is Q, which is holding the dividend value. M register is going to hold the divisor value. We have to take an accumulator. The initial value of the accumulator will be 0. And n is the number of bits in the dividend. So whatever dividend you are taking in the Q, those number of bits will be the value of n. And that much steps we have to take in the algorithm. So the value of n is going to decide the number of passes in the algorithm there. Then each pass will be having an step 2, in which what we have to do, we have to first of all see the sign of an A register. If it is 1, then we have to shift left the content of A and Q register, and we will perform A equals to A plus M if A is equals to 1. Otherwise, we will shift left the content of A and Q, and we will perform A equals to A minus M. That means we have to add the 2's complement of M to A and store it to A here. Okay. So step 2 is clear. We have to see the sign bit of accumulator. If it is 1, we will shift left the content of AQ, and we will perform an addition operation which is equals to A plus M. That means accumulator plus divisor will be added. Otherwise, if the accumulator is having a sign bit equals to 0, then we will shift left the content of A and Q. But For this condition, we will perform the subtraction, that is a equals to a minus m, which means we have to add the 2's complement of m to a and store it to a there. Now, the step number 3 will be if the sign bit of a is 1. Okay, so whenever we are shifting left the a and q, then the qth index, that is 0th index of the q register, will be set to 0 if a is 1, the sign bit of a is 1. If the sign bit of a is 0, then the 0th index of the q will be set to 1. So as I told you, what is q with index 0 means? This is the least significant bit of the q there, which we have to set there. After this, the step number 4, the value of the counter n is decremented by 1, and we will follow these steps till the value of counter becomes equals to 0. Now, if the value of n becomes 0, then go to next step. Otherwise, repeat from step 2. That means we have to repeat it from the step number 2 there. Step 6, if the sign bit of a is 1, then a equals to a plus m, and as the step number 7 is what? Step number 7 will give us now the register q contains quotient value and a contains the remainder value there. So we will now see this particular storing division method with the help of an example there. So let us take an example. So here we are going to have a things on non-restoring method there. So this is using non-rest perform this division algorithm. So what we are doing, we are dividing that quotient will be 3 and 3 threes are 9 and the remainder will be 2 there. Okay. So we are going to have these two values 3 and 2 in the Q register and in the A register after the final step of the algorithm there. So Q is equals to dividend. So in this case, Q is 11, which will be set to the binary equivalent of this Q will be equals to 8011 there, and one bit extra bit we are taking 0. Okay, so this is the binary value of 11 there. Then we have divisor, which is equals to, in this case, 3. The binary equivalent of 3 is 0, 0, 0, 1, 1. Okay, this is the binary value 3 there. As we know that we have to perform subtraction. That will require the value of minus 3. So we will take minus m, which will be equals to minus 3. So taking the 2's complement, so we will take 2's complement here. Okay, so we are taking the 2's complement, which will be equals to 1, 0, 1, 1, 1. Okay, so this is the binary value of minus 3 in 2's complement form there. So we have q, we have m, accumulator, the initial value of accumulator will be 0. The value of n is going to be 5, as the number of bits in the dividend is equals to 5 there. Okay, so in dividend there are 5 bits. Okay, that's why the value of n is equals to 5. So these are all the initial steps that we have to initiate. Now we will begin with the algorithm steps, that is pass number 1. Okay, so in the table we will be holding the value of accumulator. We are having q and we are having the value of n. So in the initial step, the value of n is equals to 5, q is equals to 11. So the value is 0, 1, 0, 1, 1, and accumulator in the initial step is equals to 0. So 1, 2, 3, 4, 5. Okay, so all these are the initial values. Okay, now what the second step says, that what we have to check, we have to check the value of a, the sign bit of a. If the sign bit of a is 1, we will shift left the content of a and q and we will perform a equals to a plus m. Otherwise, If A is equals to 0, then we will shift left the AQ and we will perform subtraction there. Okay. Now let us go with this thing. So the initial the sign bit of A is 0. Okay, it is 0. So sign bit of A is equal to 0. So shift both A and Q register. Okay, shift both A and Q register, considering them as 1. Okay, so now we will shift left, so performing shift left operation. Shift left. Okay, shift left. So shifting left. This will give us value uh, 0, 0, 0, 0. The value of this 0 will be shifted here in the accumulator. So this is 0, then 1, 0, 1, 1. Okay, 1, 0, 1, 1. And as of now, the qth index, that is the 0th index of the q, will be left blank. Okay, and this value will be decided on the basis of the operation and the value which will be get in the accumulator there. So now, as the sign bit was 0, so we have to subtract. So A equals to A minus M. Basically, what we are going to do, we are going to perform A equals to, we are going to perform A equals to A plus minus M there. Okay, so we are going to add in accumulator the minus 3, which is 1, 1, 1, 0, 1 there. So what we will get? 0 plus 1, 1, 0, 0 plus 1, 1, 1, 1. Okay, this is the thing here. So now what after the operation, what is the sign bit? Sign bit is 1. Sign bit is sign bit after subtraction. After subtraction is 1. That's why the q 0th index value of the q, that is the LSB will be 0. Okay, will be 0. So now the what we will be having, we are having 1, 1, 1, 0, 1 in the accumulator, and the value of q register will become 1, 0, 1, 1, 0. Okay, this is what I perform in the pass 1 there. Now let us move on to the this is the whole step which we have performed. Okay, so we have first checked the value of accumulator, which was equals to 0. So when the value of A is 0, q considering them as 1, so we have done the operation of shift lefting, and then the value of this 0th index of the q is left blank there. Okay, then after that, this was the step number second which was going on. Okay, this is the step number second which was going on. Then we perform the subtraction, and after that we see the bit of the A register, that is the sign bit of the A register, which is 1. That's why the 0th index of the Q register becomes 0 there. Now let us move to the pass 2 there. Okay, because now the value of n will be decremented. So value of n will be decremented, which is equals to 4. So it is not equals to 0. We have Q register and we have A register. Now we will look on that. A register was holding 11101. So A register was holding 11101, and Q register was holding 10110 there. Okay, this is the things which we are having in the A and Q register after pass number 1. Okay, now again, what we will see? We will see the sign bit of A. Now the sign bit of A is equals to 1. So we will perform shift left AQ. Okay, so we will shift left. So 1 1 0 1. This one will come here. Okay, this one will come over here of the qth, that is the MSB of the Q will come into the accumulator there. Then Q register will be holding 0 1 1 0, and this will be left blank. So as the sign bit was equals to 1, now we will do addition. Okay, A equals to A plus M. We will do A plus M. So we are going to add plus 3 into it, 0 0 0 1 1 there. Okay, so now we will add 1 and 1 0. 1 is carry, 1 and 1 triple 1 1 1 1 1. Okay, this is what we get after the. So now see that the accumulator, the sign bit of accumulator, now sign bit of A is 1 after addition process, after additions. So Q naught will become equals to 0 here. Okay, that's the 0th index will become 0. So now this the value of accumulator is 1 1 1 4 times 1 0, and Q register will become 0 1 1 0 0 there. Okay, this is the pass number 2. Okay, these steps. Now let us move on to the pass 3 value. So pass 3. Now the value of n will be decremented by 1. It becomes 3. So the value of n is not equals to 0. Then we have Q and we have accumulator register there. So let us see the value of Q, 0 1 1 0 1 1 0 0, and accumulator is having 4 times 1 0 there. 4 times 1 0. Okay. Now in pass number 3, the value of accumulator is equals to 1. So shift left AQ as sign bit is 1, as MSB of A is 1. So 1 1 1 0 0. Okay, triple 1 0. This will 1 go out, and triple 1 0. This 0 will come into A register. Now 1 1 double 0. This will be left blank here. Again, as the sign bit was 1, so we will do an addition process. A equals to A plus M. Okay, so we are performing this A equals to A plus M. So 0 0 0 1 1, we are going to add it. So 0 plus 1 1, 0 plus 1 1, 1 plus 0 1 1. Okay, now all the bits of accumulator are 1, that is the sign bit is also 1. So now sign bit A is 1 after addition process. So Q naught will become 0. Okay, so this will be 1 1 1 1 1 and 1 1 0 0 0. Okay, so this is the value of accumulator and Q register, value of accumulator and Q register after pass number 3 began. Now we will decrement the value of n. So pass number 4, pass 4, N, Q, and accumulator. Okay. So in the pass 4, the value of N will be decremented by 2, so it is not 0. We will repeat all the steps. The value of Q is 111000, 111000, and the value of accumulator is 1111, 1111, 1111. 1111. The sign bit is equals to 1. Sign bit of A equals to 1. So shift left AQ. So we will shift left 1, 1, 1, 1. Okay. This one of Q register will come here 1, 000, and this will be left blank. Zeroth index of the Q register will be left blank. Now we will perform A equals to A plus M. As the sign bit of A was 1, that's why we'll perform this thing. So we are going to add 3, 00011. Okay. So this will going to give us 1 and 1, 0, 111, 1, 1 and 1, 0, 1 and 1, 0, 1 and 1, 0, and 1 will be discarded. The carry will be discarded there. Okay. So now the sign bit A is 0. So the least significant bit of Q, that is Q naught, will be set to 1. Okay, we will set it to 1 there. So accumulator in this pass will become 00010, and Q register will become 10001. Okay, set to 1. That is after the pass 4. Okay, now let us move on to pass number 5. That is the last step. Pass 5. The value of N will be decremented. Previously the value of N was 2. Now it will become, again the value of N is not equals to 0. So we will repeat all the steps. Q and A register. Q is holding now 10001. 10001, and A register is holding 00010. Okay, 00010. So let's begin. As you see that now the sign bit of A is 0. So we will first shift left AQ register. So 0, 0, 0, sorry, 0, 0, 1, 0, and this MSB of the Q will be shift left to the accumulator 0, 0, 0, 1 there, and this will be left blank. So whenever the sign bit of A is equals to 0, we have to subtract M from the accumulator. So we are going to perform A equals to A minus M there, or we can say that A equals to A plus minus M there. So we are going to add the 2's complement of the 3 there. So 11101. This we are going to add. So 1 and 1, 0. 1 is carry. Okay. 1 is carry. So 1 plus 0 is 1. 1 and 1, 0. 1 and 1, 0. 1 and 1, 0. And 1 will be discarded there. Now, as you are seeing that, now after subtraction, the sign bit of A is 0. So the that is Q naught will be equals to 1 there. Okay, this we will set over here. So in this step, accumulator will become equals to 00010, and Q will become 00011 there. Okay, so this is in the pass number 5. Now in the next, value of n will be decremented. So when you will decrement the value of n will become equals to 0. So we don't have to repeat the steps there. Now we will stop this algorithm. Q is holding, as the Q is holding 00011, and A is holding 00010 there. Okay. So if we convert these values of A, that is 00010, to the decimal, this will come out to 2, and Q will holding 00011. So this will become 3 in decimal. So as we were performing 11, we were dividing 11 by 3. So 3 threes are 9, and remainder will be 2 there. So see that quotient, the value of quotient is holded by Q after the final step, and the value of remainder is provided by the accumulator. Okay, this is the non-restoring method, which was no requirement of the restoring step there whenever we have the unsuccessful attempt, or we can say that whenever there was a negative value in the accumulator. Okay, then we were performing the restoring method in that particular thing. So that particular operation is not required there. This increases the efficiency of the non-restoring method there. So this is how we perform all the steps of the non-restoring method there. So let us see once again the algorithm. So what the algorithm says, that first of all we have to initialize the Q, which is equals to dividend. The M is going to be acting like a divisor. The initial value of accumulator will be equals to 0, and the value of N will be decided by the number of bits in the dividend. Now in each pass, what we were seeing, first of all we were seeing the register A. If the sign bit of A register is 1, then shift left the content of AQ, and we will perform the subtraction addition process. If the sign bit of A is equals to 0, then we have shift left the AQ, and we have performed the subtraction process. And how we have done the subtraction process? By taking the 2's complement and adding that 2's complement to the A register. After this operation, that is of addition or subtraction, whatever is the value of A, we have to again see the sign bit of A. If it is 1, then we will set the 0th index of the Q, that is the SB of the Q, equals to 0. If it is equals to 0, then we will set the LSB, or the 0th index of the Q, to be 1 there. Then every pass the value of n is decremented by 1, and it goes on till the value of n become equals to 0. So if the value of n becomes 0, then go to the next step. Otherwise we have to repeat all these steps from the step number 2 there. Okay, if the n bit of A is 1, okay, let us suppose here in this case in the past 5, we were having the sign bit equals to 0. Okay, we were sign bit having a 0, so this was the final answer. But if in this case, if the sign bit of A comes out to be 1, Okay, then we have to perform the addition process, that is a equals to a plus m, which will going to give us the final answer there. So now after this final step, the quotient is holded by the q register, and the value of a is giving us the remainder value of the division method. So this was the non-restoring algorithm. These are the references which you can go through for the Boost algorithm there. Those Tannenbaum and Frozen. Thank you.